So now we're going to look at how to write a polynomial function from its zeros and also how to find a relative minimum and maximum value. So here we have the factor theorem. Now this theorem is not completely new to us. We have looked at something similar to this before. Now what the factor theorem says is that the expression x minus b is going to be a factor of a polynomial if and only if this value b is a zero of the related polynomial function. Now this makes sense, right? Because if 2 and negative 2 are zeros of my function, then that means, how did I get 2 and negative 2? Well, I must have started with x minus 2 to get x equals 2, and started with x plus 2 to get x equals negative 2. Right? And so when I multiply these two back together, I'm going to get my original polynomial function. And remember, something times something means that these guys are factors of the original expression. So we are going to write a quartic polynomial function in standard form with the zeros negative 2, positive 2, and 3. Now if I have negative 2 as a zero of my function, then I must have started out with x plus 2 as a factor. So remember, whenever b is a zero, x minus b is going to be a factor. And if b ends up being negative, this guy right here will be a plus sign. Okay, so that's according to the factor theorem. Now I have negative 2 twice, so I'm going to write x plus 2 twice. Then what represents positive 2 is x minus 2. And what represents the 3 is going to be x minus 3, and that's all going to be equal to y because I'm talking about a function, okay? And your y can go on either side, obviously. So now all that we need to do is multiply. So lots of multiplying going on, but nothing that we aren't capable of doing. So remember, when you're multiplying many different polynomials together, it doesn't really matter where you start because it's all multiplication, but I normally start from the left and move towards the right. So I'm going to go ahead and distribute this out. And once you have it distributed, you're going to then combine like terms before you start multiplying again. So at each step, you should rewrite the rest of the equation. You should stop and combine like terms, and then continue to multiply once again to the next binomial. So now we're almost done. We just need to combine like terms. Now combining like terms, I like to scan through the problem, see everything that has the same degree. So x to the 4th, use that. Once I use it, I like to cross it out. These guys match up. Cross it out. These guys match up. Cross it out. And only one constant term. So this is going to be our polynomial function that had the zeros negative 2, positive 2, and 3. So if you're crazy curious as to what that function would look like, this is what it would look like if you graphed it. Notice we have zeros at negative 2, we have a 0 at positive 2, and then this here will be 3. Now in the last example we saw that negative 2 was a 0 2 different times. So when we wrote the linear factors out, we had x plus 2 quantity squared to represent that it happened twice. Now when this occurs, we have a special vocabulary for that. We say that that 0 has a multiplicity of however many times it appears. So if b is a 0 and it has multiplicity of n, where n is some number, then that means x minus b is going to appear n times as a factor. So let's say that 3 is a 0 and 3 has a multiplicity of 4. Well, then that means x minus 3 to the 4th power is going to be a factor. So x minus 3 is a factor 4 different times. So the multiplicity of a 0 is going to change the way the graph looks at that 0. So if the 0 has a multiplicity of just 1, which means it only appears once, then the graph is going to be very linear at that point, okay? Which means it's going to resemble very closely to a line. Now, if the graph has a multiplicity of 2, then the graph is going to look more quadratic at that point, which means it's going to be more of a U shape like a parabola. If it has multiplicity 3, it's going to look more like a cubic function, which means it'll more have that type of shape, and so forth. If it had 4, it would look like a quartic function, okay? So this just kind of helps us figure out what our graph should look like at those particular zeros. So here's an example. Here's the graph y equals x squared, x plus 2 times x minus 4. It's already in factored form. Now, since x squared appears twice, that means 0 is going to be a multiplicity of 2. So on the graph, if you look at 0, since there's a multiplicity of 2 at the 0, this curve on the graph is going to resemble a quadratic function, which it does. It kind of looks like a parabola, right? Now, -2 only has multiplicity of 1, which means that at that point, -2, the graph looks very linear. It's just a straight line. And at the 0, 4, it has multiplicity of 1. So at that 0, it also looks very linear. So here I have a function, and I want to first figure out what the zeros of this function are going to be, and also the multiplicities for each of the zeros. And then I want to kind of talk about maybe what the graph is going to look like at these particular zeros. So looking at this, if I set each term equal to 0 and solve, x squared equal to 0 and solve, well, 0 is going to be my solution, and since I have a square here, I know that I will have 0 multiplicity of 2. It appears twice, right? And looking at the next term here, x minus 2 squared. Squared means it appears twice, so I know my multiplicity is going to be 2, and if I actually solve this, I would get x equals 2. So my 0 is 2, and I have a multiplicity of 2. And then the last term, x plus 1. All right, if I solve that, I just get x equals -1. Therefore, -1 is a 0, and it only has a multiplicity of 1. If I could spell multiplicity, right? Now, what would our graph look like? Well, that means at 0, okay, if I wanted to maybe do a little quick sketch of this, this is not going to be fantastic, okay? At 0, I know that it will be more of a parabolic shape, okay? So it's going to be more of a parabola shape at 0. And at -1, it's going to have more of a linear shape. And then at +2, it's going to have more of a parabolic shape again. It's going to look more like a quadratic function. So the multiplicities just help us figure out what the graph should look like, and it helps us sketch these functions better. So here's a sketch of the last graph. So you can easily see that we said at 0 we have a multiplicity of 2, and it should look more like a parabola, and it does, right? That's a parabola shape. At 2, we should have a multiplicity of 2, which means this guy should look like a parabola, which it does. And then at -1, we have multiplicity 1, so it should look very linear. And this does indeed look very linear, just looks like a line through the 0, -1. So we talked about maximum and minimum values whenever we studied parabolas. We said that if my quadratic function opens up, then I'm going to have a minimum value at the y coordinate of the vertex, right? And if my parabola opens down, then I'm going to have a maximum value at the y coordinate of the vertex. Now with these higher degree polynomial functions, we have more than one turning point, right? With the parabolas, we only have one turning point. That's why we only have one max or one min. But when we have multiple turning points, we now get what is called a relative maximum or a relative minimum. So these relative max and mins are going to be our maximum and minimums on the smaller neighborhood of values of x, okay? So relative maximums are going to occur when my function is going up and then starts to turn down. So when I have a turning point that is increasing and then decreasing. minimums occur when I'm going down and then going up, so they're going to be a minimum value. Now remember, when we're talking about max and min, we are only referring to the y value of that coordinate. Because a function can have multiple turning points, we are going to be able to have a relative maximum and a relative minimum on the same small value or interval of x. All right? Now I can only have one of each, but I can have both. So let's look at this first example and let's figure out what the relative max or min is going to be. Or both, right? Because I could have both. Now looking at this graph, maximum value, I want to look at what my relative maximum value is going to be. Well, I'm going to be looking at this interval here from here to here, and I want to figure out where is my function achieve the highest y value. Well, that's going to happen up here, right, at this turning point. Now, again, we are not using graphing calculators, so this will just be an estimate. I just want you to kind of eyeball it when you look at the graph. So what value of y is being achieved right here? Well, that's at maybe, approximately 2. So I would say my relative max is going to be at 2. Now my function will also have a relative min, and I want you to notice that this function has a 0 at 0 and a 0 at 2. Now the smallest y value this function is achieving on this interval here is going to actually be 0. Now what that means is even though it happens twice, I only write it once, our relative min is at 0. Okay, that's the smallest y value that the function is achieving between this small interval here. Now looking at part B, again, I'm just going to focus in on this interval here, right, from here to here before it starts going off into infinity. So from here to here, I want to know what's the highest y value it achieves and what's the lowest y value it achieves. So our relative max is going to be the highest y value, and that's going to be up here at 1. All right, and our relative min is going to be at the lowest y value that we achieve, and you can easily tell on this graph the lowest y value is down here. Now remember, we are estimating, so that's approximately negative 3.5. All right, so there are my relative min and max values by looking at the graph of the polynomial function. So here you're going to work backwards. You're going to go from your zeros 0, 2, and 3 to your cubic function in standard form. Now the only hint I'll give you is that if 0 is a 0, then that means I started out with x minus 0 as a linear factor, which is just simplifies to x. I want you to look at these two graphs, and I want you to tell me the relative min and relative max. So remember, you can have both for each graph, but you're only going to have one maximum and one minimum value. And it is okay to go ahead and estimate. So these are going to be estimates. For this problem, I want you to tell me what the zeros of the function are going to be, and I want you to state the multiplicity of each of the zeros.